I'm going to go ahead and throw this section in there and just do a few examples involving functions. Again, you can read the pause the video and read this, and then you can start the video and listen to me after that. But basically here we have this is a riverbank, and we're going to put a fence around that riverbank in a rectangular fashion. And we know that if we have a total of 500 feet of fence right here, so it tells us that. So we know if we let X be the sides extending from the riverbank and L be the side parallel to the riverbank, then I know that X plus L must equal 500. So 2X plus L must equal 500. And then what I would do there is I would solve for L and try to get L in terms of X. And the reason I want to do that is because the area here is actually, since this is a rectangle, it's just the length dimension times the X dimension. And of course you could have used W here. But so L times X is the area, and what we want to do is we want to maximize that area. So we're going to maximize LX, and when we maximize it, we're going to multiply L times X, but we can replace L with this right here, minus 2X plus 500. And so I'm going to put minus 2X plus 500 in place of L, and I'll get minus 2X plus 500 times X. And then when I distribute the X, I'm going to get minus 2X squared plus 500X. And then that's a quadratic function that opens down, and therefore it has a maximum. So we talked before about how to find the maximum. Just do the minus b over 2a formula. So that would give me minus 500 over 2 times negative 2. And if you calculate that out, you're going to get 125. And then if you go back over here, let's see, no, right here. If you go right here, you can actually plug that X value of 125 into here to get your length, which is negative 2 times 125 would be negative 250, and then negative 250 plus 500 would give me 250. So the length is 250, so the distance from the bank would be 125 feet, and then the length parallel to the bank would be 250 feet. So the dimensions would be 125 feet by 250 feet. And if you want to find the area that the maximum area, you can actually find it two ways. The harder way would be to take the 125 and plug it back into the function to find the area. But actually, you know that area is length times width, so you could just multiply 125 times 250 and get it. That's an easier way to get it. So the dimensions that maximize area 125 by 250, and the maximum area is 31,250 square feet. Now, the next example, we've got a steel drum here that's in the shape of a circular cylinder, and it needs to have a volume of 100 cubic feet. And right here it says express the amount A of material required to make the drum as a function of the radius R of the cylinder. Now R would be right here from the middle of that top to here, so that would be R. Now you're going to need a couple of formulas, but the total area, you know, the surface area, when I say area, the surface area of this cylinder, or can I say can for short? The surface area of this can is actually the area of the top plus the area of the bottom and the area of the side region here. Okay, and so the area of the top and the area of the bottom, those are just circles. And so you know the area of a circle is pi r squared, right? So the area of a circle is pi r squared, so the area of the top is pi r squared. The area of the bottom is pi r squared. So those two areas add together to give me 2 pi r squared. The catch is, how do I find the area of the side of the can? Well, what you can do is, suppose you cut it right down here and then unfolded it. Well, if you did that, then this dimension from here would just be the height. Okay, so the dimension from here to here would just be the height of the can. And this dimension from here over to here, all that would just be the circumference of the circle. So the circumference of the circle is 2 pi r. So basically the area of this piece would be, since now it's a rectangle, would just be 2 pi r times h. And so that would give you the area of that rectangle. So the side area is actually 2 pi r h. So put it all together, the area of the side is 2 pi r h. The area of the top plus the bottom is 2 pi r squared. So now we know a way we can represent the area in terms of radius and height. Now, the problem that I'm going to run into, though, is I've got too many variables here. In this function, I have 2 independent variables, radius and height. I need to figure a way to eliminate one of those. And that's where this information here comes in. It gives me the volume. Okay, now the volume of a circular cylinder, you can look that up, and that's pi r squared h. And since they told me that the volume needs to be 100, I can actually take that equation, and you'll notice down here I can take that equation, and I can actually solve this for h by dividing both sides by pi r squared. So all I have to do is just divide both sides by pi r squared. So just divide this by pi r squared, and then divide this by pi r squared. And then, of course, what will happen is, over here, all that will cancel, and I'll just get h, and here I'll get 100 over pi r squared. Now, how does that help me? Well, the way that helps me is, since that's h, let's go back to this formula that I developed earlier, formula for the surface area, 2 pi r h. Well, now I can eliminate this h by replacing it with 100 over pi r squared. So I'm going to take the h and I'm going to replace it with this value, 100 over pi r squared. And now if I multiply 2 pi r times this, well, 2 pi times 100, that's 200. And then the r over r squared, well, r goes over r squared and gives me r in the bottom, and then the pi's are going to cancel. So I just get 200 over r, and then plus 2 pi r squared. Okay, now if we were in a calculus class, what we would do is we might minimize this surface area. So we might figure out a way to minimize this surface area, but we can't do that in an algebra class because this is not a quadratic function. This is a rational function. So we can't really go any further with this particular function. But we can answer the second question. It just says, how much material is required if the radius of the drum is 3 feet? Well, all you have to do for that, if the radius is 3 feet, just put in 3 here, and then put 3 here. So everywhere there's an r, put in 3. So you get 200 over 3 plus 2 pi times 9. And then I just grabbed a calculator and figured that out. And I came up with 123.22 square feet. Okay, we're going to do one more. We're going to take a box, and it's going to be made by a 20 by 20 piece of cardboard. Okay, so basically what we're saying here is this is 20 by 20 from here to here, and then it's 20 from here to here. Okay, so I have 20 by 20, and what we want to do is these little red squares, we're going to cut these little squares out, and then what that'll allow me to do is it'll allow me, like right here, this blue portion, I can turn it up, and then I can turn this blue portion up right here, and then I can turn the blue portion up over here, and then the same thing over here, and basically I can make a box. Now it won't have a top, but I can make a box like that. So the question is there a way to express the volume of a box in terms of the little corners that I cut out? Well, the little corners are going to be, I'm just going to call them x by x. Okay, so I'm going to cut out x by x. Now, here's what's going to happen. If I cut x out here, if I take x away from here, and I take x away from here, then the dimension that I'm going to have for my box is actually going to be 20 minus 2x, because the total distance across is 20 units, and then this is x and this is x, and that's going to be cut out, so I'm going to have 20 minus 2x, and that's going to be true on all four sides. So the box is going to be 20 minus 2x on each side. Now, the height of the box, since I'm going to turn this side up right here, and remember that dimension is x, so when I turn that up, it's going to give me a height of x. So the dimensions of my box are actually 20 minus 2x by 20 minus 2x by the cutout, which is x. So all I have to do is multiply those together, and I can take 20 minus 2x times 20 minus 2x times x. And then when you multiply 20 minus 2x times 20 minus 2x, you're just squaring a binomial, and so I got 400 minus 80x plus 4x squared, and then you multiply by that by x, and you get a function that represents the volume. You get a function here that represents the volume in terms of the cutouts. Now, you might not think that's too important, but see what that allows me to do. If you said you wanted to cut 1 inch out, I could just plug 1 in here and I could tell you the volume. If you said you wanted to cut 2 inches out, I could plug 2 in for x, tell you the volume. If you say you want to cut 3 inches out, I can plug 3 in for x and tell you the volume. Okay, so we could keep drawing different values until we got the box, found out, what length I should cut out, what size corners should I cut out so that this box has a maximum volume. That's kind of the long way. In calculus, there's a better way to do it, but we could do it by trial and error there. Now, one thing you don't want to do is you don't want to go up to 10, because if you cut out 10 by 10 corners, well, think about it. If you cut out a 10 by piece here, and then a piece 10 by piece here, then basically that's half of the width. So basically you would have cut out, the corners would have basically, you would cut out the whole piece of cardboard if you did that. So anyway, there is a limit to how high x can go. And so these little problems are just to give you some examples of how you can express functions and use functions in applications. So that's pretty much it on that, and we're going to go to rational functions in the next section. So have a good one.